In this video, we're going to solve some basic indefinite integrals. So what do I mean by basic? Well, up to this point, we've learned the meaning of the term antidifferentiation. So the idea that we want to find a function whose derivative is the given function. And we've seen some examples of finding the antiderivative of a function. So we were introduced to the term antiderivative at the end of Calculus 1. And then so far in Calculus 2, integral calculus, we've learned about the notation as well as a new naming convention that was adopted for antidifferentiation. So this notation here was used to indicate find the antiderivative of the given function. So here's the given function, and this symbol, this elongated S symbol with the dx on either side of the given function indicates that here this is saying find the antiderivative of this function. And furthermore, you can say that this means that you want to find the antiderivative of this function, but another name you can call this, and this name is more commonly used, is that this is called an indefinite integral. So you can say that this is an indefinite integral, or it's commonly said that you're integrating this function. And so in the previous videos, we learned the details of how all of this developed. What is the meaning of this elongated S symbol? Why is this even called integration? Why is the elongated S symbol, which represents infinite sum in the infinite summing tool, the definite integrating tool, the main area where the term integration came from, why is that even used here as a symbol to represent find the antiderivative of a given function? Okay, but now that we have all this background information established and we have the official notation for antiderivative, one of the main things we're going to do for the rest of Calculus 2 is just learn how to find antiderivatives. And this is where we're going to start. So we're starting with the most basic antiderivatives. And these are called basic because, so here's a table of antiderivatives that we were given in this section. And what makes these basic is that you don't have different types of functions multiplying each other, as well as you don't have compositions of different types of functions. Now, adding or subtracting together different types of functions still keeps it as a basic indefinite integral, since as shown here, if you have an indefinite integral with different types of functions added or subtracted, you can just separate that into separate indefinite integrals that are added or subtracted together. But as long as you don't have different types of functions multiplied together or composed within one another, then what we'll be able to do is either use our knowledge of differentiation to just naturally figure out what the antiderivative is on our own, or we could just reference this table to get the antiderivative. Now, when it comes to more complicated functions, we'll have to use other techniques, which we'll learn in later sections. Okay, and before we get started, a couple of more things to note. First, so after this video and the upcoming videos, as we move past the fundamental theorem and the definition of a definite and indefinite integral, I'm going to transition away from the term antiderivative and just start referring to, something like this as just integration. Okay, and then also just remember, so what is the use of finding antiderivatives? Learning the skills to find antiderivatives. Well, for indefinite integrals like this, which is just like for differential equations, there's value in finding a function whose derivative is a function you know, okay? But then not just that, though, definite integrals. To evaluate a definite integral, you need to first find the antiderivative. So that's why the majority of what we do in Calculus 2, integral calculus, is learn all about the different techniques and skills that are needed to find antiderivatives. Okay, so now let's get started. Let's evaluate this indefinite integral. Okay, and so first, based on this property here, we can separate this into two separate integrals. So we can write this as okay, now based on this property here, the constant multiple property, we can bring this 7 out in front of the integral. Okay, so now we can use the power rule for integration. So that's this rule here. And just note that the n value is not, that doesn't have to be an integer. It's any real number, positive or negative, other than n is equal to -1. Okay, so we do x to the n plus 1 over n plus 1. And why does this make sense? Because if we take this derivative, you bring down the 2.3, 2.3 divided by 2.3 is 1, and then 2.3 minus 1 is 1.3. All right? And now just to show you this, I guess we could say plus, we'll call it C1, right? The indefinite integral of this function is, this is correct. You know, you have to put that constant if you want to be technically correct, right? Okay, plus 7 times, so we do x to the 3.5 divided by 3.5. And what we can do is, so 3.5 is 3 1/2, that's 7 halves. Okay, now plus C2. Okay, so simplifying, this is, and then we've got, okay, but this C1 plus C2, that's just a constant. So we can rewrite this as, I'll bring this 1 over 2.3 out as a coefficient. Like that. And so you can see we didn't really need to write this, these C1s and C2s like this. And you'll get a natural feel for when you don't have to write this a constant like that, because you know it's going to end up in the end going to be combining with another constant. All right, and so this is the most general form of the antiderivative to this function. And what does that mean? So we know that for an antiderivative, an indefinite integral, there's multiple different functions that result in the derivative of the function we're given. And so the idea is when we compute an indefinite integral, we want to give the most general form so that that general form includes all possible functions whose derivative are the given function. And this constant does that, is sufficient. And the idea is, I've talked about this before, but so if you've got f of x dx, okay, so what is this equal to? It's capital F of x plus c. The idea is when you're finding an antiderivative, you're going to first have an expression that has x terms in it. So like here, we've got these two x terms added together, you see? And then so that's the first part of the antiderivative. It's either one term or multiple terms added together, but every single term is in some way a function of x. And that's what capital F of x is. And once you have capital F of x, so like you found, again, I want to make this clear, you found this, it's an expression that could have one term in it or multiple terms if, added together or subtracted together, but each of those terms has at least like one x in it. None of those terms is a pure constant. Okay, that's what capital F of x is. And when you take the derivative of capital F of x, you get the original function. But then all you need to do to make what you have general for all possible functions is just add a c to the side of that capital F of x. That's it. So you see how this is capital F of x in this situation? This is an expression that has two terms in it, but each of the terms has an x value in it. So that's the capital F of x. If you take the derivative of capital F of x, you get the function. But to make this as general as possible, to include all possible curves whose derivative is the given function, you just add a c to the back end of capital F of x. Okay, so we can write this as, this is x to the 5/4 dx. And so now we just use the power rule for integration. So What is 5/4 plus 1? That's plus 4 over 4. All right, so we've got, this is x to the 9/4 over 9/4. Okay, so that's it. This is capital F of x. This is the expression with one or more terms that where every one of those terms has x's, at least one x in them. And when we take this derivative, we get x to the x to the 5/4. Okay, so now to finish this problem, we just add a c to the back end of capital F of x. And so what we get is 4/9, and I'll put it back into this form here. There you go. Okay, we can separate this into 3 separate integrals. Okay, now we can use the constant multiple rule to bring constants out to the front of the integral. Okay, here we know that just the integral of 1 dx is x, because the derivative of x with respect to x is just 1. Okay, here we use the power rule for integration, so this is going to be 1/3 x cubed. Okay, here we use the power rule for integration. This is going to be 1/4 x to the 4th. All right, so there's the capital F of x. It's these 3 terms added together. All 3 terms have x's in them. So to finish this, we put plus c on the back end. All right, simplifying. And there you go. That's the indefinite integral. Okay, here let's distribute this. So u squared, or no, it'd be 2u squared plus u plus 8u, so 9u plus 4. Okay, now we can separate this into 3 separate integrals. Okay, now we can bring constants out front of the integrals. Okay, now we can just use these two. We can use the power rule, and this is just, we know it's going to be u. So it's 1/3 u cubed, 1/2 u squared. Okay, now here's capital F of u. So to finish this, we just put a constant on the back end. So now simplifying. That's the indefinite integral. Okay, so here we can write this square root of t as t to the 1/2. Okay, now we can distribute this t to the 1/2. So t to the 1/2 times t squared is t to the 5/2. Okay, then so 3t times t to the 1/2 is 3t to the 3/2 plus 2t to the 1/2. Now we can use the power rule for integration. Now we can separate this into 3 separate integrals. Okay, now we can bring the constants, these constants out front of the integrals. Okay, now we can use the power rule for integration. So here we've got t to the 5/2 plus 1, which is t to the 7/2 divided by 7/2. Okay, here we've got t to the 3/2 plus 1 would be t to the 5/2 divided by 5/2. And then here we've got t to the 1/2 plus 1 is t to the 3/2 divided by 3/2. Okay, so simplifying, oh, and then there's a constant at the end of this. So, and there you go. Okay, here we can separate this into the sum of 3 terms. So x to the 1/2 divided by x to the 1st is 1 over x to the 1/2. Okay, we can separate this into 3 separate integrals. Okay, we'll leave this as 1 over x, and we'll write this as x to the minus 1/2. Okay, so here, this is the natural log of the absolute value of x. Make sure you put the absolute value. Okay, here, using the power rule, minus 1/2 plus 1 is 1/2. Okay, x and then plus c. So we've got natural log of the absolute value of x plus 2 root x plus x plus c. Okay, we can separate this into 2 separate integrals. Okay, the derivative of cosine of x is minus sine of x, so the integral is going to be minus cosine of x. Now, hyperbolic sine, I need to consult the table on that one. So hyperbolic, what was it, sine or cosine? Hyperbolic sine is just hyperbolic cosine. Okay, so each of these would have their own constant, but again, those constants combine and you just get one arbitrary constant on the back end of the capital F of x. So there you go. Okay, we can separate this into 2 separate integrals. Okay, here we'll have 2 theta, and then tangent squared. Let's see. Well, we know that there is they give us an antiderivative of secant squared, okay? And so with that, with trig properties, we know that secant squared theta is equal to 1 plus tangent squared theta. So tangent squared theta is secant squared theta minus 1. Okay, so we can separate this into 2 separate integrals. Okay, so the integral of secant squared theta is tangent theta. Okay, 2 theta minus theta is theta, so we've got theta plus tangent theta plus c. Okay, let's distribute this 2 to the t. All right, let's separate this into 2 separate integrals. Okay, so what we can do is, we'll leave this as is. Here, we can write this as, this is 2 times 5 to the t power, right? Because you here, like ab to the t power is a to the t, b to the t. So you see this is 10 to the t power. All right? Now, we can consult the table for the integral of exponentials, but since we know that like the derivative of 2 to the t is 2 to the t natural log of 2, then the integral's going to be 2 to the t over natural log of 2. Because now let's take this derivative. This derivative is 2 to the t natural log of 2, but then you divide out the natural log of 2, you're left with just 2 to the t. Same thing here. Now, this is your capital F of t. Just put plus c at the end. All right, let's think about what is sine of 2x as far as a trig identity. That's 2 sine theta cosine theta. Well, 2 sine x. 2 sine x cosine x. All right. Let's bring the 2 out front. All right. The derivative of sine of x is cosine of x. There you go. That's it.